All right, so let's go over the examples that I mentioned in the written part of the class. So the main command that will plot a vector function in the 3 dimension is this space curve, which has a suggested name, right? So the only difference is that notice that the notation here for the component form of a vector are not like in the book with less than or equal, greater than or equal to as the markers left and right, but just straight brackets, right? If you see it here. So that's how Maple understand that that's a vector. So on paper, of course, you will write it as 1 plus 5t, comma, minus 4t, comma, 2 minus 3t. So that's one remark. So the first example is a line, nothing too spectacular, right? I mean, straight line. I just picked a random here domain for t, but you should imagine this is an indefinite, I mean, an infinite line, right? As with t going through all real values. Of course, if you want to restrict yourself to a specific line segment, as I show here on this example, for example, if you want line segment from 1, 1, 1, let me do that in the text mode here, and 3 minus 2, 4. On paper, of course, remember the formula is scalar product 1 minus t times the component vector that points to the first point plus t scalar multiple the vector that points to the second point, 3 minus 2, 4. Again, remember, don't confuse the vector that points to a point with the point itself. And of course, if I do the scalar multiplication, let me see if I can make this bigger. And if I simplify this a little bit, then you're going to end up with the components 1 plus 2t, 1 minus 3t, 1 plus 3t. Again, a line with the only difference that it precisely starts at the starting point 1, 1, 1 and ends at 3 minus 2, 4. This is one of the examples done on paper before. So this moves on a cylinder. Let's see. Let me actually change the color here so that it's easy to see. Right? This is when x and y move on a circle, right? Because x equals cosine t, y equals sine of t means x squared x squared plus y squared is equal to 1, right? Because it's the same as sine squared t plus cosine squared t equals 1. So if I see this picture, and then z goes to 0, right? Because as t goes to infinity, as t increases, z goes to 0. So therefore, you have a spiraling motion. If you see it from above, you basically hide the z coordinate and just see the variation of x and y, which is on a full circle. Here's another example. Let me see if I can modify this a little bit because I don't know if you can see it clearly, easily. This is like a more general, I mean, it's a slight modification of an example like the previous example. The only difference is that here the spiral is not going to be on a cylinder, like a circular cylinder, but on an elliptic cylinder. So in other words, if you want to identify the surface this curve lies on, we can still exploit the fact that cosine squared plus, in this case, yeah, cosine squared plus sine squared is equal to 1, but you need to isolate them first, the cosine and sine. So notice the x coordinate is 3 cosine of t. Y is t third, and then z equals 4 sine of t. So that tells me that x over 3 is equal to cosine of t. Then z over 4 is equal to sine of t. And then if I square both sides, oops, I didn't want to do that. If I square both sides, I get x squared over 9 plus y squared, z squared over 16. Equals 1, which is an ellipse. So y goes to infinity. So again, you're going to have a spiraling motion along the y-axis. So this will be basically an elliptical cylinder along the y-axis. All right. So now the problem is when you run these examples with Maple, again, let me change the color. Sometimes it can be misleading because Maple distorts the kind of scales the range of each axis so that it fits a nice picture. But like, for example, here you see the range here is like 10,000 or 100,000. So it's obviously distorted compared to the vertical axis here. And the misleading part is that if I look at it from the side, instead of seeing an ellipse, I actually see a circle, but it's really an ellipse. If you want to see exactly how it looks like from both sides, I mean, at a scale, then you have to select the option scaling constraint. Now, the problem with this, of course, is that you have to play around with the function a little bit because everything can be so squished. You have to change the coordinates and modify a little bit so you can maybe shrink the domain a little bit. Just play around with the numbers, both the domain and maybe the function itself, so you can see it better. So you see, when I see it from the side, well, no, this still doesn't look like doesn't look like much in terms of an ellipse. Let me see if I can make it 20. It still distorts this a little bit. Let me see if I can actually modify the function itself. Anyway, it's an ellipse. It's not a perfect circle, but it's not that easy to actually convey this, unfortunately, with Maple. Let me see if I can distort the. Oh, I think I know what the problem is. I have to actually select this again because the default was unconstrained. Anyway, so I hope now it's clear. Okay, so the cross section of the cylinder is an ellipse, right? So similar example one before. I forgot that whenever I actually start over the command, it's defaulted again to unconstrained. Of course, you could also put the options here. Constrained in the command so that you don't have to worry about getting back to the default setting. So let's see. Okay, let's do this one as well, the last one. This is when the curve lies on a plane because x plus y is equal to 0. Because you already have sine squared and cosine squared here in the vector function itself. So if you see it from the side, you can clearly see that the curve lies on an actual plane. Make the domain a little bit smaller. X and y can vary periodically because they are given by cosine and sine, but the whole motion in line is on a plane. So I want to finish with one interesting example, which I didn't do on paper before. Sometimes you can have a completely closed curve, even though t varies from minus infinity to infinity, because the entries are all periodic, as you can see here. All values repeat themselves. Let's see if we can actually figure out what the curve looks like mathematically before I run it with Maple. So we have x equals cosine of 2t. Now, if you remember a trigonometric formula, this is the same as cosine squared of t minus sine squared of t. And because y and z are cosine of t, sine of t respectively, you could say that then x is actually y squared minus z squared. And on the other hand, again, y and z vary among them. I mean, together lead to the fact that y squared plus z squared is equal to 1. So in this case, basically the surface, excuse me, the curve is given as the intersection of two surfaces. One of them is x equals y squared minus z squared, which is actually a hyperbolic paraboloid along the x-axis. If you look at the quadratic formulas, you should see that as well. Independently, y squared plus z squared equals 1 is going to be a cylinder along the x-axis as well. Remember, the x being missing in this equation means it takes any value. But that therefore it generates a full cylinder. So let's look at these two surfaces together to see how they actually generate a curve at the intersection between the two. All right, so I hope you see the saddle kind of shape, the hyperbolic paraboloid along the x-axis over here. And then it's cut through by this cylinder. And if you look at the way they intersect, you can clearly see actually it forms a closed curve in this particular case. Okay, so if we actually sketch the space curve itself, then we have the confirmation, right? That this is the way it looks like. Obviously, if you just see the curve, it might not be easy to realize that it comes from the intersection between a cylinder and a hyperbolic paraboloid. Might lead you to the hyperbolic paraboloid shape because it's kind of like a saddle, but it's not easy to see that it's actually is cut from a cylinder. So I think that's all for today. I'll see you next time.